we're going to take a lattice, and we're going to say, in this lattice, we have P available lattice points. And we have an occupation, which is psi. So the number of sites that are really occupied is psi P, right? Because psi is the fraction that's occupied. Okay, then I'm going to ask the following question for you. What is the entropy of this lattice occupied with a fraction psi? And if you remember principles of statistical mechanics and thermodynamics, you have just to count the possibilities. You just go and count. I have P sites available, and I have psi pi, psi P objects to distribute in these boxes. Everybody did that once, I'm sure. Even in high school we do that. How many red balls I can put so how many configurations? If you do that, that's the configuration number. The entropy, thanks to Gibbs, is this relation. And then you just write this, calculate the entropy, and this entropy depends on the occupation number, of course, or the occupation fraction. This is a straightforward type of relation, right? I mean, this is permutations. Combinatory analysis, right? So then I calculate the entropy here. So I have the entropy. And the entropy depends on the number of sites, of course, but depends essentially on the occupation fraction. And I'm going to do some approximations like, oops. Oh, okay. So let's keep this here. Now, yes?
How many sites do you think you have?
P.
Right. But as a number?
Oh, that's depend on the size, but you can have many thousand. I mean, I don't know. Is it normally the distance between is typically on the order of the wavelength of light, because lattices are created by interference of beams, right? But so you can have many lattice points, yes. No, and normally you can drop thousands and thousands of atoms in those lattices, and you do all kinds of experiments, as you're going to see in the other talks. So, but now let's see a free Bose gas. Suppose I have a free Bose gas. What's the entropy of this free Bose gas? This is in all the books like Huang, Landau, Patria, Heights. No, what's the one we use in São Carlos? Heights. Heights is the electromagnetism book. Right? Jesus Christ. Okay. Sometimes you have to shake to accommodate the lattice points. So now, if you imagine a free Bose gas, this is the entropy. I'm not gonna. This is everywhere. You can calculate. So if I have any particles and I'm below the critical temperature, this is what I have. Okay? So this is the entropy of a free gas, and I calculate the entropy of a lattice. If I do adiabatically, when I finish my lattice, what's the entropy of the system? Has to be this. Right? If I end with something different of this, I don't have a Bose condensate there. Of course, we're not taking into account interaction. This is a hyper-diluted gas, because the interaction is not the point. The occupation of the lattice is the point. So remember that the number of particles is basically the psi times p, because it's how many particles I have there. I have p sites, a fraction psi occupied.
That number is some universal number?
What number?
1.2.
Oh, it's some approximations, but it's basically, yeah. But I took constants and I put, because otherwise I can't deal with the other expression. I cannot make a identity. That's why I gave up all the possible constants there. It is.
But it not depend of the
No, this is, no, it's a free gas. So you do in a box and then you make the box go to infinite. Okay? So this is the number. Remember, then I'm going to substitute. So this is the entropy of a free Bose condensate gas. This is the entropy of lattice. They have to be equal. Because if I do adiabatically, entropy is preserved. So I just solve graphically. The optical lattice has this entropy. Of course, if it goes to 1, as you know, occupation, entropy goes to 0, right? And if you have 0, also is 0. If you have only one possibility, logarithm of 1 is 0, entropy is 0. You all know that. Then I just cross with the free gas. And there is one point here, which means 0.54 or 55, it's about. So, if I have my lattice more than half occupied, when I adiabatically remove it, I end with a condensate still. If I have less than that, I have a cold gas, yes. Maybe quantum gas, yes, but not condensate, right? Okay, this is first exercise. Let's go for the second exercise because I said nothing about fermions. And you know, they exist. Nature is not so kind for them, but they exist. So what I want to do is calculate the Fermi energy. Because again, half of the talks you're going to see from now on, I'm going to speak about Fermi energy. Yes?
Before you go on, I have a question.
Yes, please.
Consider a lattice.
Microphone.
No, I can.
Oh, but the tape can't.
So if you have a lattice with each atom, one atom per side, okay? Then you know that starting with a BC, you have a Mott insulator. And I mean, in this case, you have that the fluctuation in phase are much bigger because the fluctuation in the number is almost 0. So this is almost related to what you've shown. I mean, it should be related in some way.
Boy. I don't know if the phase fluctuation will be related to the entropy I calculate. It eventually can, because once you have a thermodynamic function of the system, you can recover the fluctuations, right? So in some sense, I think if I express well the entropy in terms of the thermodynamic variables I choose here, I can recover, and probably they are related somehow. But this is a kind of straightforward calculation. I mean, just show that to keep the entropy, if you really do adiabatically, you need to have a minimum occupation number. Otherwise, you don't end with a condensate at the end of the process. Because normally they produce lattice, and they study, and then they destroy the lattice and investigate. Some experiments are done that way. And we just want to know that if the occupation number is not right, then you may end with something different. Okay? Now, let's go to the fermions. I want just to estimate the Fermi energy to show you, compare with the bosons. So, Fermi energy, as you know, if I have a box, I just put all the levels, and I put 2 particles in the box by Pauli principle. And when I end my any particles, that energy is the Fermi energy. And this is also calculated almost everywhere in the world. If you can get a quantum mechanics book that doesn't have this, you know, I give this present, which is here, and it's for the one of you. Okay, so this is normally what we do is we know the relation of energy. We start to pile up particles, and we end with this Fermi energy for a box. Okay? Now, box, we don't have box in the lab. We have harmonic oscillators. So let's go for a harmonic oscillator. Oh, that you may not find so easy, the Fermi energy for a harmonic oscillator. But maybe there are around because everybody works harmonic oscillator. I'm sure that the experimental groups or the theoreticians know very well this. So let's consider harmonic oscillator. This is the energy of the harmonic oscillator. And I'm going to just normalize energy in units of h bar omega, because here, energy is just the addition of numbers. Okay? So energy here will be 0, 1, 2, 3, 4, because I normalize by h bar omega. And then the question is, if you have this energy, what is the Fermi energy for a n-particle system. You have to add up. So, but now it's not that easy. Suppose you have an energy E. You may have many possibilities of states which have that energy. So suppose I have a E. Remember, E now can be 1, 2, 3. Right? So I have a E00, 0, and Nx, Ny, Nz are the quantum number for the 3 directions. I'm doing 3-dimensional. But can be E minus 1, 1, 0. So you can just list all the possibilities, right? And you can count. And what's very interesting, when you do this counting, you end that the number of states for a given energy E is just this series. Is the sum from 1 to E of I plus 1. And everybody can do this series. So you do this series, and then you come here and you find out, there is some approximations, and you find out what is the Fermi energy. This is for a harmonic oscillator. I put here the critical temperature for a boson system. Fermi bosons are very different. If I define a Fermi temperature as the Fermi energy divided by K, turns out that the Fermi energy and Bose critical temperature, they are very similar. What's very interesting, they scale the same way, so it shows that the scaling of the energy and the temperature is just a property of the potential. But the root cubic of 6 is like what? 1.5 maybe. And this is 0.94, so the Fermi energy, and if we can call a boson energy, a Bose energy, which is the critical temperature, are very close. So to reach the degeneracy in a Fermi gas or in a Bose gas, you have to reach almost the same temperature if you have almost the same number of particles. That's interesting. Nature was bad to fermions, but not that bad. Make them to be almost equal on the temperature scale. Okay. Now, in this calculation I did, it's very easy to introduce an anisotropy, and you show that the Fermi energy scales with the anisotropy the same way. And what is this? Oh, we're going to jump all this. Sorry. Where is my last part? Oh, here's. Sound. Ketel already spoke about sound velocity, and I'm going to speak more, so let's give up that. We hear yesterday about healing length. And I just want to show what I think it is, healing length. Okay? So, healing length is the following. Let's consider a Bose gas in the Thomas Fermi approximation. Very strong interaction. You know, we saw that the wave function comes and goes to 0. Boom. Because it's the mu minus the harmonic oscillator. Goes to 0 sharp. If it goes to 0 sharp, what is the... Oh, this is a continuous function. Wave function never is discontinuous. Don't worry. But the derivative is not continuous. And worse, the second derivative is not continuous. That creates a problem for us, because the second derivative of the wave function is basically energy, momentum. No? Momentum squared is the kinetic part of the energy. So, if I have a divergence on the second derivative, I have divergence on the kinetic part of the energy. Right? So that doesn't seem right. And in fact, this is just an approximation. Wave function never will do that. There will be a length where the wave function going to smoothly go down. And this region, this length, this characteristic length, where the wave function goes smoothly down, is the healing length. And we can calculate. Because we know that at that point, that situation, the energy is not infinite. The energy is about the chemical potential. This is the energy available there per particle, in order of magnitude. So we can estimate what is the healing length? And then we just take this, which is given by this, and we make equal to the chemical potential. This gives us what is the characteristic healing length for a system that has some number of particles, a density of particles, and a scattering length. Because this is just due to interaction, okay? To have a zero healing length, which means a wave function comes and boom, you need an infinite scattering length for this approximation. And that doesn't exist, really. I mean, you can have big, but... Okay, so, in fact, even in that approximation, the wave function will come and whoop, and this whoop is the healing length. And yesterday, Wolfgang showed vortices. And vortices, you saw the dark part where there is nothing there. So the wave function goes to 0 there. And goes, it should be like, choom, but it's not because of the healing length. So the typical size of the vortices is also the healing length. And this I put in quotation because I took out of a paper from Jean Delibard. They're going to be here. You can ask him. And if he say no, then he wrote wrong. Because the healing length is the typical length in which the superfluid recovers from a sharp change. Okay? It's written there. So I just import. So this is the concept of healing length. And you're going to hear also healing length many times, I hope. And you know now what it is. Okay? So let's see what else we have. Nothing. And it's exactly 10:30. So I thank you very much for sitting here this morning. If you have any questions.
Thanks, Professor.
Thanks. Now, you may have a chance for a question before coffee. Let me tell you that the course that, when I talk with them, I suppose to give you introduction to many things because you should hear about this before other talks. Okay? And Ketterle yesterday was very informal, gave a general, but now he's going to build up some more concepts on that. And of course, what I show you is present in all the presentations we see. So if you have any questions that I can answer, I'm not a theoretician. I don't solve Gross-Pitayevs every day, but I have people that can help me if I need. But you can ask a conceptual question. Maybe I can.
What you have in your pocket?
Is a present. Well, that's depend on the questions. That depend on the. This will be later. It's here. I can't. Oh, look. It cracks. It's wrapped in a present paper. It's no peanuts. No questions? Yes. Shh.
In the problem of the optical lattice. In the problem of the optical lattice that you solved, you have the optical lattice and you have an atom in each side, and you are going to turn off the lattice adiabatically, and you want to know what do you have to do in order to have a condensate at the end of the process. To end. But my question is, if you turn off the potential, you will not have any potential at the end, and you don't have any ground state to occupy macroscopically, and how can you speak about a condensate in that condition?
Good question. You see, normally we say that a free condensate is a condensate in an infinite box, and the approximation we do, which is the thermodynamic limit, we make the number goes to infinite, the volume goes to infinite, and the density is finite. So this is what I did here. But I consider that this macroscopic object is big enough that I can consider as infinite. Okay? And this is what people do in the lab anyway. So even though you have a free, it's still a particle with a single wave function behavior in a way that you expect a condensate to behave. And they produce this free condensate, and then they interact with part of it or with another condensate, right? This would be a kind of free expanding condensate. Yes. I used the other one.
So you will know that you have a condensate because you will observe that sharp distribution.
No, you
in the
start
moment
with a
space.
condensate and you put all the particles in the ground state of that potential. If I have one particle there and I put the lattice down, everybody knows that that's a condensate, right? Because you have all the conditions, the number of particles per cubic de Broglie wavelength is the right one and everything. Okay. So maybe he have an addition for me.
I think there's an additional trap. There is a harmonic trap in this case, or not?
No. This is just a free.
Just free.
Yeah,
Just
the way
the outcome
you
lattice.
can have that. You can turn
Just
off
the
the
outcome
lattice and
lattice.
have but you do the same calculation for the harmonic oscillators. Okay.
So you have just the optical lattice. You don't
Yeah.
have a
No, here is an
harmonic trap in
optical
this case.
lattice that you adiabatically, slowly destroy, and we want to leave with a gas, which is like if I had a condensate in a potential and I take the potential away, I still have a condensate there.
Yeah, okay.
In fact, that's the way they measure everything. Almost nobody measures in situ, right, with the potential on.
I would comment that in general, crossfit is the non-local.
Okay.
Locality.
Yeah. Oh, you want me to comment on?
Yes, it experimentally measured some non-local effects.
On the condensates? Not that I know.
On this I know dipolar condensate is
Yeah, well,
local effect should be important,
yes, non-local.
non-local.
Yeah,
Because
but
in
I-
general, it's not differential equations. It is non-local, non-linear shredding.
Yeah.
Crossfit
I can't answer with some
Because
knowledge.
all this equation with approximations that local interaction between two atoms.
That's right.
In general can be with some.
You understand the question? No. The way we, like the first part where I said in one point of space, the atoms interact with the local density. This is a local effect. But when you write the total wave function, in fact, one particle here, has a wave function that goes there, so this is a kind of non-locality type of effects in there. But I don't know how to answer if people has observed that. We are trying, São Carlos, to excite coherent modes of a condensate, which is the solutions of the Gross-Pitayevsky. And maybe, even though my hope is see effects that go beyond Gross